Uh, Hi, this week we're happy to have Menke Liu from Jenny Hoffman's group. She's going to talk about what's, I think, a very hot topic in the topological materials, quantum information, is that if you combine magnetism with topological insulators, there's predictions that you can isolate Majorana fermions and other novel states, if you like, to manipulate quantum information. The field is fascinating because it combines material science. You need the new materials, and what she'll be telling you now is how you can figure out what goes on inside the material. And so I look forward to your talk.
Thank you.
And thank you very much.
Thank you, Bob. The nice introduction. And hi, everyone. I'm Menke Liu. As Bob introduced, I'm currently a postdoc working in Jenny Hoffman's group. I joined later August last year, and today I'm going to present my graduate school work on visualizing interplay of Dirac mass gap and magnetism and nanoscale in magnetic topological insulator. So I believe we have plenty of time for questions, so please feel free to stop me anytime for the in-person participant. And yeah, I also very prefer to have interactive presentation. So okay, let's see. Okay, so before I dive into the science, I would like to first acknowledge a group of researchers that is involved in this work I'm going to present. So my advisor, Professor Ken Shi from UT Austin, and both my teacher and my collaborator, Alan McDonald from UT Austin as well. Both Ken and Alan gave me enormous support during my grad school career. And my collaborator, Chao Lei, who is a theorist and contribute most of the theory work in this talk, and a few junior grad students, Sue, Yanxing, Li, Lisa, they have shadowed me for a couple of years while I was a grad student, and Jia Qiang, who is our crystal provider from Oak Ridge National Lab. Okay, so in 1980s, the discovery of quantum Hall effect really marked a turning point in condensed matter physics, and Klaus et al. Have discovered that upon applying a large external magnetic field and both the Hall resistance, the core resistance can have a quantized value, and the longitudinal resistance can have a zero value. This means that the charge transport along the edge can be dissipationless. So this really brings lots of excitement to the field from a technology point of view, because this dissipationless charge transfer can be very helpful for develop new generations of electronic and spintronic devices. However, the observation of quantum Hall effect can only be observed at external magnetic field and also at really low temperature. This prevents the further development. But another turning point happened in 2013, marked by the discovery of quantum anomalous Hall effect. In the quantum anomalous Hall insulator, people discovered that the presence of quantized Hall conductance or resistance and dissipationless edge channel does not require the external magnetic field, and this is an advanced step in terms of developing the dissipationless devices. Okay. The magnetic topological insulator is one of the best platform for hosting quantum anomalous Hall quantum anomalous Hall effect. And let's start with common topological insulator. Common topological insulator, the Dirac surface state, presented as illustrated here by this KE space and real space illustration, does not have a gap. However, when we have magnetism, the exchange interaction between the Dirac surface state with the magnetism can open up a gap, and this gap is called a Dirac mass gap. And in accompanied with this, there will be a dissipationless edge state, and that edge state is called quantum anomalous Hall edge state, and that is what we are dreaming about, and to utilize this edge state in the electronic devices. Okay, so in the early days, people designed the magnetic topological insulator by doping the topological insulator with some external magnetic atoms such as chromium. So here, this discovery in 2013 by Cuizu Chang, they discovered that in a chromium-doped bismuth antimony telluride, they can see this quantum anomalous effect, which signified by the zero magnetic field plateau Hall conductance or resistance. And however, in this extrinsic magnetic topological insulator, the quantum anomalous Hall operating temperature is extremely low. It's only about 30 millikelvin. So the next big challenge would be, how are we going to develop a high temperature quantum anomalous insulator, or how are we going to observe the quantum anomalous effect at a high temperature? Okay, so then the recent discovery in intrinsic magnetic topological insulator, as represented by manganese bismuth telluride, provide a promising platform. So in the magnetic bismuth telluride, the manganese atom, as illustrated here, they form a well-ordered lattice, and they couple ferromagnetically within the setup layer and anti-ferromagnetically with adjacent setup layer. So because the manganese atom here, they form a well-ordered lattice, they reduce the disorder effect that is contributed by the random dopant in the extrinsic magnetic topological insulator. And as a result, it may increase the quantum anomalous effect operating temperature. So the MBT can be grown either by flux method or chemical vapor transport method. So here, this is the bulk sample that was grown by Jiaqiang. In this work is quite large. The flake is quite large. And as I said, it's an antiferromagnetic material, and the new temperature is about 24 Kelvin. It's quite high compared with, those extrinsic MTI. Okay, so people has discovered the presence of quantum anomalous effect in odd setup layer thin flakes, as represented by this work in 2020. You can clearly see at zero field that the Hall conductance or resistance is quantized. Okay, so far it looks pretty promising, right? But there are still some controversies. The controversy is, for example, one of the biggest controversy is that this quantum anomalous effect is not universally observed. So in two of the work I presented here, you can see that at zero field, this Hall conductance or resistance, it's not quantized. It's far from the quantized value. And only you apply a large enough magnetic field, those plateau will exist. And same for the other paper as well. And another controversy is the presence of the Dirac mass gap. As I have mentioned in the beginning, the exchange coupling between the Dirac surface state with the magnetism should open up a gap. It breaks time reversal symmetry and open up a gap at the Dirac point, which is a prerequisite for the presence of quantum anomalous effect. However, even this requirement is still, under highly debate. So it's not clear yet. There has been some RPAS work. These two work. Some RPAS work claim that they have seen this gap to surface state, and the gap value was extrapolated by fitting their energy distribution curve with some Gaussian curve, and then they can extrapolate the energy value. But other RPAS results did not see such a gap. They see this gap. They see a gapless state, a very clear gapless state below the new temperature. New temperature is 24 Kelvin. Here is 10 Kelvin. Below the new temperature and above the new temperature, up until room temperature. So they see an intact gap that is independent of the temperature and also independent of the cleanness of the surface. So even for air cleaved sample, they still see this gap. This gapless surface state. So, okay, so what are the reasons that lead to so much controversy in this family of material, and what are the difficulties related to this material? So here, I organize them as below. So this material, first of all, is heavily n-type, as I have shown in the RPAS result. All the RPAS results shows that the Dirac point is actually far below the Fermi level. It's about 300 millivolt something like that, 300 millivolt below the Fermi level, meaning it's heavily degenerate N-type, and that can lead to a short Dirac fermion lifetime, which maybe broaden the spectral observation. And also, we can infer that those disorder or N-type dopant, they can be a little bit random, and their distribution in homogeneity can lead to a local chemical potential fluctuation. And also, in addition to that, there has been report the MBT, manganese bismuth telluride. Usually, the growth of MBT can be intermixed with a few other compounds like bismuth telluride, manganese telluride, which are both stable. So the growth can be very tricky to only get MBT without any BT or MT intermixing. APAS and transport are all like microscopic characterization, and they cannot avoid averaging effect. And all of this can contribute to a broadened and smeared feature in the topological surface state and make it really hard to distinguish the size of the gap or even the presence of the gap. Okay, so to disentangle this mystery, what we did is we combined a molecular beam epitaxy to grow the film layer by layer and to also control the defects concentration to make it low defect regime and as intrinsic as possible, meaning that we can move the Fermi level into the gap, and then we can see the presence of the gap clearly. And also we use scanning tunneling microscopy and spectroscopy, which is a microscopic visualization technique. And then we can get rid of the averaging effect and can really tell in atomic precision how the gap changes or whether it's present or not. Great. So, okay, so now we get to our result. So let me recap again about the manganese bismuth telluride structure. Here is, this is the lattice structure. You can see that the manganese atom formed well-ordered lattice, and we call each unit cell as the top layer. It consists of tellurium, bismuth, tellurium, manganese, tellurium, bismuth, tellurium, and you can think of it as manganese telluride intercalate into bismuth telluride and form a manganese bismuth telluride. And so on top of this lattice structure, I also highlighted two native intrinsic defects, which we call a manganese bismuth antisite or bismuth tellurium antisite. For manganese bismuth antisite, I mean a manganese atom replacing the bismuth atom, as shown here, and the bismuth tellurium atom similarly, a bismuth atom replacing tellurium atom. And manganese bismuth antisite is known as acceptor defects, and bismuth tellurium antisite, or there's another one, bismuth manganese antisite, I didn't highlight, but similarly, it's a bismuth atom replacing manganese atom. They act as donor defects. They are the most common native defects present in this material. So we like to start from bulk study first, because that's what has been reported or studied intensively in this family of material. So we can see that this atomic image, relative large scale atomic image, present about 5% of manganese bismuth antisite, which appear as dark triangular suppressions, and about 0.2% of bismuth telluride antisite, which appear as bright circular protrusions. So this broad background fluctuation, I believe you can see that it doesn't seem to be very flat uniform, right? So that is related to the large amount of bismuth manganese antisite, which is far below the surface because they live in the bismuth manganese layer. It's a little hard to see by STM, but their high intensity or their high concentration can be inferred from this STS data. I can take a look. So from the STS data, we can see that the Dirac point is actually about 270 millivolt below the Fermi level. And that is consistent with most of the APAS results so far, and also consistent with other people's STS on these box samples. So this heavily N-type nature of the box sample make the gap signature very smeared. And as a result, it's really hard to quantify or even tell the presence, even hard to tell whether the gap present or not, because this it never goes to zero. The density state never goes to zero, right? So, so then what we did is we go to our MB grown samples. We successfully grown MBT, manganese bismuth telluride, on graphite substrate. We also succeed in graphene substrate. But for the most of the STM result here was focused on graphite substrate growth. And a line cut across our flake, as presented here, help us identify the thickness of the suitable layers, which is really important because we know that each suitable layer corresponds to 1.35 nanometer. And if it is other compositions such as MT or BT, which would have a different thickness, and this cross-section, help us ensure that our measurement is done on MBT and not BT or other chemical compound at all. So also this inset, as shown here, the inset shows the atomic image taken on this MB grown sample, and which shows about 4% of manganese bismuth anti-side. A similar amount of manganese bismuth anti-side, but the background is quite flat and clean. And that is related to significantly reduced amount of bismuth manganese anti-side, and we don't have any bismuth tellurium anti-side at all. So the reduced amount of bismuth manganese anti-side is a little hard to see from STM because it lives far below the surface, but can be inferred from our STS result. So first of all, let me start from a low defect of first tube layers. Here, this result is taken on first tube layer thin film, and with a set point of 0.6 volt, which is relatively high at 4.3 Kelvin, which is below the near temperature, we first see a sizable low conductance bias range. But this low conductance bias range doesn't represent a gap. It actually represents a significantly reduced amount of density of state near the Fermi level, which is confirmed by our DFT calculation. Our DFT calculated density of state projection to the top four atomic layers. They roughly correspond with each other. When we found that when we reduce the set point bias to be lower, to be 0.2 volts, and a clean exchange gap appears, as shown here, which is about 120 millivolt, and that is also consistent with theory prediction. So, yeah. Any questions so far? Yeah, go ahead. Yeah, good point. So the Dirac point was defined as so there is not an exact Dirac point because after we turn on the magnetism, we will open up a gap at the Dirac point, but the Dirac point is still defined as before turn on the magnetism. So, but anyway, here we see that the Fermi level lives within the gap. So if the Dirac point should be somewhere in the middle of the gap.
So now it's like a 4s layer, right?
Yeah, first tube layer.
That means it's anti-ferromagnetic.
It is anti-ferromagnetic. That's right. It's not a problem. And but the time reversal symmetry is still broken for first tube layer. So first tube layer, fifth tube layer, they all have a surface gap.
I guess my confusion is that what's the difference between like the previous RPS measure and what you're measuring here? I know that is bulk.
Oh no, previous RPS measured on bulk. They also measured on thin film as well, but the paper I presented is on bulk. You can see the previous RPS measurement, their Fermi level relative to the Dirac point is pretty high. So here they also define it as a Dirac point, but they actually open up a gap. So, it's just a convention, but this is a Dirac point gap. This is how they define as Dirac point gap. Yeah, so I guess the improvement for us is we can eliminate the amount of defects and get really intrinsic sample. So you can see that the Fermi level position is inside the gap. And this density of state really goes to zero, meaning there's no density of state. That means there's a gap. So the biggest improvement is actually from the MB grown result. So you can really get intrinsic samples. Okay, so a little bit of technical spectra that is specifically for STM people for my group. Okay, so as I said, maybe I did not convince you that the tip to sample distance may change but here we did the ZV spectroscopy characterization of tip to sample distance. You can see that there is a discontinuity at this bias, and that signifies a tip to sample distance is increased at this bias because the tunneling current was kept constant, and that is a signature of reduced amount of dense state when it go across past this threshold energy. And also we did the IZ spectroscopy to characterize the tunneling barrier to make sure that below and above the threshold energy, we are at a normal tunneling barrier. The tip does not crash. It's still at tunneling regime. So we did the IZ spectroscopy. So I constant at some specific tunneling bias, I can see that the tunneling barrier constant or decay constant kappa is still within the normal regime, meaning there's still vacuum tunneling barrier. Yeah, this is to carefully check our spectroscopy. That is correct. Anyway, so what we did further is to make sure that this gap is magnetic related, we raise up our temperature to be 77 K. In this case, it is above the new temperature, and we still see a similar sizable low bias conductance region. But when we zoom in, and we can see this gap disappears. The disappearance of the gap above the new temperature is another evidence for the gap is magnetic related origin. So, okay, so similarly, we did the thickness dependent surface state gap measurement on different setup layers or thicknesses, and we can summarize it here as below. And together with our DFT calculation, DFT calculated result, which shows a good overall agreement, given the tendency that the DFT usually will underestimate the gap size. But overall, they agree pretty well. So yeah, a very brief summary, I think. Upon having a nice sample, meaning that we can really eliminate the amount of defects and move the Fermi level to be within the gap, we observe a clean gapped surface state, and we resolve this the hot debate in the field. And we also carried out a thickness dependent gap size measurement. Okay, so yeah, I'd like to pause here a little bit and to see if there's questions. Yeah.
So between 4.3 Kelvin and 7.7 Kelvin, you have more than
That's a really, really good question. Is also what we want to do for a long time, but unfortunately, no, it's like STM, right? You either at liquid nitrogen temperature or liquid helium temperature. Yeah, it's a little tricky.
I'm sorry, could you repeat the question for the people on Zoom?
Okay, sure. The question is, do we have temperature dependent data points between 4.3 Kelvin and 77 Kelvin? And the answer is no. Unfortunately, we don't have, because the limitation of our instrument, we can either at a liquid helium temperature or liquid nitrogen temperature. And but the side note is we have characterized the new temperature for our sample, which is 25 Kelvin. It has some variation from sample to sample, but the new temperature is consistent with what has been reported in literature. Great. So okay. So then after we observe a clean gap, the next question we'd like to address is, so okay, if gapless, why? This question. So how come in the field there are so many people observe the gapless states, surface states? And to answer this question, we use scanning tunneling spectroscopy spatial mapping to visualize the local Dirac mass gap variation. So okay, so still let's take a look of our clean and clean low defect samples on first layer, and the data points. Okay, the spectra corresponding to data points is as follows. You can see that although regarding on their different positions, the small features may vary a little bit from point to point, but overall the gap size remain very neat and very uniform. And most importantly, the Fermi level is actually inside the gap. That means this is this is an intrinsic sample. So the low defect, meaning that the Fermi level lives within the gap, and we see a clean gap with uniform sizes. However, this feature changes drastically when we go across a high defective sample. When we see here, this figure is 3 subtubular high defect sample. When we draw a line cutting across a locally defect free region as represented by point number 1 and point number 2 to a highly defective region as represented by point number 6, we can see the evolution of those spectroscopy. At those local defective free region, we still see a finite but shrink gap. But when we progress to the defective region, you can see this gap was suppressed and eventually it was collapsed. And accompanied with this collapse is they also have a linear V-shape kind of feature. So we can conclude that in the high defect region, the gap can be suppressed or collapsed. And this point to the significance of anti-sites in suppressing this exchange coupling. Go ahead.
Does the different defects have a similar contribution to the gapless feature of like the one you mentioned? There's some donors and also some receptors.
Yeah, you are. That's also a good question. So as I said, STM, the anti-site defect we can see is mostly manganese bismuth anti-site. The bismuth manganese is far below the surface. It's hard for us to make correspondence, and bismuth tellurium anti-site doesn't quite exist in this film in our sample growth. So the relation we want to build is mostly related to manganese bismuth anti-site. But that's a good point. Considering that our sample is pretty intrinsic, right? If you agree, this is because the gap still lives. Sorry, the Fermi level still lives inside the gap. It's pretty much an intrinsic sample. So later on, when we do this model calculation, we think that it's the N-type dopant and P-type dopant are pretty much compensated with each other. Yeah. So next would be, how are we going to understand this suppressed Dirac mass gap by those defects? So to do that, we performed a couple Dirac model together with the DFT calculation. And so here, let me introduce the couple Dirac model first. The couple Dirac model considers the Dirac cones live on the top and bottom surfaces of each subtubular layer, and we allow the coupling for those Dirac cones within the same subtubular layer as represented by this delta S, or with adjacent subtubular layers across the van der Waals gap as represented by this delta D. And here the I and J denotes for the number of subtubular layers, and M is the exchange potential, which can be written as such. So delta IJ denotes for the I Dirac cone coupled with the Dirac cone on the J's layer. So here, let's reduce or simplify our model by only consider the important parameter, which is delta S, delta D, and JS and JD. Sorry, I forgot to reintroduce JS and JD. JS is the Dirac cone, is the exchange coupling between the Dirac cone with the magnetism or magnetization. JS meaning same layer with the same layer or the adjacent layer, meaning JD. Okay, so if we reduce this Dirac model to be only considering delta S, delta D, JS, JD, we can simplify this model to as such. So we get rid of those high order coupling or hopping term. And in this case, the exchange potential M can be written as, in the ferromagnetic case, can be written as JS plus JD. In the anti-ferromagnetic case, can be written as JS minus JD. And we can, from this model, we can write the EK relation as, using those parameters. I can choose some high symmetry points by choosing KZ equals 0, gamma point, or KZ equals pi over A to be the Z points. And and then we know the energy at those specific high symmetry points as a function of those parameters delta S, delta D, or MF. Now, how are we going to extrapolate those parameters? So we use a very smart way to compare them with DFT calculation. So, there has been DFT calculation as well, or we can do our own DFT calculation. And then we can extrapolate those energies at those high symmetry point and compare them with our model. And then we can extrapolate those important parameters, delta S, delta D, the hopping term between Dirac cones, or the exchange coupling term between Dirac cones, and the magnetization, MF. And then let's take a look at the result first. So here is our calculated result. In the thin film case, we can see that except for the first topol layers, for all the other topol layers, the the DFT calculation compare pretty well with our model calculation. So they compares, reasonably well. Let's see. So okay, so then after we have such a Dirac model, in our specific experimental study, we adapted this model to take into account of those magnetic anti-sites defects. The model was first proposed to only be the case of pristine thin films, but let's now take a look at after we consider those magnetic anti-site defects. So it has been reported that the bismuth manganese anti-sites living in the bismuth layer, it couples antiferromagnetically with those in the manganese layer. So they couple antiferromagnetically. And as I mentioned before, because in our case, our film is pretty much intrinsic, so we consider pretty much well compensated, meaning that the bismuth anti-site, the amount of bismuth manganese anti-site is the same as manganese bismuth anti-site. So those defects will alter those coupling parameters as listed here. But then now, how are we going to get those parameters? So this parameter should not be the same as those samples without any defects, right? So what we did is we first carried out the DFT calculation, choosing supercells with some specific number of anti-site defects. And we can adjust the supercell size. We can also adjust the amount of anti-site defect size, and then we can simulate the density of anti-sites. And then we can, using similar methodology, we can compare our DFT calculation with our model calculation, and then we can extrapolate those key parameters like hopping term delta S, delta D, exchange coupling term JS and JD. Okay, so this is our calculation result. So, okay, we can see that as a function of manganese bismuth anti-site, the exchange coupling potential MF actually decreases nearly linearly. And how about the calculated calculated gap? So we can see that with first of all, let's take a look of the ferromagnetic case. Our model calculation and DFT calculation agrees pretty well. And then the thin film case, especially the antiferromagnetic fifth topol layer case, which is of the highest interest to the field, because this is the film that people argue there could be quantum anomalous effect. I can see that with increasing of manganese bismuth density, this inverted gap shrinks. Inverted gap meaning is topological phase. And this inverted gap disappears at about 6%. And this signifies a topological phase transition at this point. So above this, above this point, then it's no longer a topological phase anymore. But if you keep increasing it to really high, and you can see there's a transition. They all have a transition. There's a turning point at about 9%. So what does that mean? That means that the anti-site defects, the exchange coupling from those anti-site defects is actually high enough so that it overtakes those from the middle of manganese layer. So it's pretty interesting. This model can capture this. And okay, so still a short summary from this calculation result. We can see from this calculation that both the Dirac mass gap and topological phase is quite sensitive to the anti-sites. And we made a prediction for the maximum density in order to observe the quantum anomalous effect. Above 6% is no longer a topological phase, so that you will not expect any, quantum anomalous effect. And we think this provides an answer for why the quantum anomalous effect is not universally observed in the field. So okay, so this is pretty much a short presentation. So the summary here is the summary. First of all, we use molecular beam epitaxy to grow the thin films of MBT layer by layer, and in a very intrinsic, low defect condition. And then we can, which allows us to observe a gapped surface states. In first topol layer case, we observe a 120 millivolt exchange gap. And we also observe that the Dirac mass gap can varies as a function of local defect density, and it can collapse at high defect region. Okay, so we used a couple Dirac model and to account for those defects. And we combine the couple Dirac model with the DFT calculation, and then we sort of provide a understanding of the topological phase transition, why it's so sensitive to anti-site defects, and why people did not observe the quantum nanoscale effect universally in the field. And okay, how am I doing in time? Okay, so okay, to look forward, here is a discussion outlook. Still, although we can achieve those as I said, those pristine samples, but how to grow them in a uniform thickness and in a wafer scale is still quite challenging. They all seems like to have some fluctuation of thicknesses, and from area to area, they may not look the same. But the power for STM is we can look around and find local clean and neat regions. But to have a wafer scale clean sample uniform thicknesses, there's still a long way to go. And hopefully, if we get rid of all those defects, then we can increase the quantum nanoscale transition temperature or observation temperature to be at least close to the new temperature. And maybe it will have, we have a hope for building a high temperature quantum nanoscale insulator-based dissipationless devices. And for I have skipped a little bit for the topological superlattices. Actually, from the couple Dirac model calculation, and we predicted that the topological superlattices can have, a different combination of MBT and BT or BS, bismuth selenide or manganese bismuth selenide. They can form different topological phases. They can form either wild semi-metal or just trivial insulator by stacking them in different order and in different ratio, like 1:1, 1 MBT, 1 BT, or 1 MBT, 2 BT, so on and so forth. In addition, there has been some very interesting prediction on the twisted MBT. Because it's vanvous, you can cleave and stack them and twist them at some specific twist angle. People predict that it can have a fractional chain insulator phase and some other very flat term bands and so on and so forth. So yeah, so this is a pretty interesting platform, but I would say for material wise, there's still a long way to go in order to have all those interesting exotic quantum phases. And yeah, we'll see what will happen next. Thank you. That's it.
Is there something special about manganese in manganese bismuth telluride, or have people tried this with other transition metals?
You mean why it's do you mean why it's MBT rather than like chromium BT or MBT? Yeah, that. Okay, so the question is, why are people so interested in manganese bismuth telluride, or why manganese is so special compared with other magnetic atoms like iron or chromium? I guess it's an interesting and good question. It's mostly related to whether the film can be grown. MBT, manganese bismuth telluride, can be understood as manganese telluride intercalate into bismuth telluride, right? There has been some special lattice match condition between manganese telluride and bismuth telluride, and turns out manganese telluride, it can have a well crystal outer surface, but I don't know if chromium telluride or iron telluride, or there may not be iron telluride. Yeah, so I think it's probably related to the lattice match condition. They can form such a well-ordered lattice.
Other questions?
I think I'm just not super familiar with this system, but can you repeat why the four layers still have the integrating and the?
Oh, no, it doesn't have quantum anomaly. I didn't say that. So don't take it wrongly. So it has it breaks time reversal symmetry. Up, down. So okay, if we apply a time reversal, then you can see that this becomes down, right? Down, up. So these two are not the same. So in this material, it breaks time reversal symmetry, but it preserves time reversal times a translation, a half unit cell translation symmetry. So if we translate by half unit cell, I mean, because of the stacking is different. So here, if we translate to one topol layer, it becomes this is down. So this two is the same. So it breaks time reversal symmetry for sure. And yeah, it opens up the gap. That's right. And people argue that the even topol layers, it can be axion insulator. Yeah, I don't want to comment too much about axion insulator because I don't know if I'm qualified for that. But yeah, but it's also a topological phase. But it opens up the gap at the surface. Both top and bottom surface, they will have a gap. Yeah, no problem. Yeah, go ahead.
Band structure wrong in quasi-particle interference, and if so, do you observe this surface state predicted or?
Yeah, that's a good proposal, I would say, using quasi-particle interference to infer or deduce the band structure. Is that what you're trying to say? Yeah, so we did not do it. But that's a good proposal. I think that's something that we can consider to do it next step. Maybe on those really high defective region is a little difficult because you can see those defect is so high. It's so high. So for quasi-particle interference, there is some optimal density of defects, but I believe maybe in some region, we can do it. Right. Go ahead.
So when you do the ending growth of this material, will they always do you do like the full deficit of all three elements, or do you like make a shutter to control the you first grow on bismuth tellurium layer and then manganese tellurium layer, or like how do you do that? Can you actually alter the surface that you terminated? Like can you actually like terminate it with some manganese tellurium layer?
Yeah. So the question is, how are we? How do we do the growth? Whether we did it like a bismuth telluride, manganese telluride anneal, or we co-deposit, or can we control which termination of the layer we have? The answer is there are many ways. In MB growth, there are generally two ways actually to do the growth. Either you can, as you said, you can alter the growth of bismuth telluride, manganese telluride, and you anneal and make the manganese telluride to sink in the middle of bismuth telluride, or you co-deposit them together. You open up the shutter for both bismuth, manganese, and tellurium, and then they form a well-ordered lattice. In our case, in this specific case, we did a co-deposition. So three of the Rosen cells, we open them together at the same time, and they deposit on the surface. Yeah, but there is pros and cons in those two methods. So it depends on which group, like which recipe the group start, and then how they are going to optimize along that way.
So I'm just curious because it seems like STM when you do the bulk cleave, it always cleave with like the bismuth tellurium, like the kind of you add with this bismuth tellurium layer, right? So when you image it, it's always like on bismuth tellurium layer, but can anyone cleave? Like, because there's no natural cleavage between that's the one walls between those central layers, and no one actually measured the manganese tellurium.
Okay, so I guess your question is whether we can get access to the manganese tellurium layer, right?
Yeah.
Okay, so first of all, we can take a look at their structure. You can see the van der Waals gap is between the tellurium and tellurium layer, right? So
Yeah.
that means naturally, if you cleave, will grow,
Always.
you will, yeah, that's right. That's right. However, I think some MB group also reported that they have seen the manganese tellurium layer. But then the manganese tellurium itself is just manganese tellurium. It somehow it doesn't sink into the middle of the BT. So yeah, I didn't see a very well, systematic study for the MT, but you can form a small patch of MT that happen to do not sink to the middle of the BT. Right.
The last question? Okay, well, thank you so much.
Thank you, Bob.
Thank you.
Thank you. Oh, there is a question, right? On the chat. Okay.
Yeah.
Let's see. Yeah, let me just read it. You mentioned dissipation, this edge mode without resistance quantum height. Does that directly mean superconducting edge? So it is topologically insulating in the bulk and topological superconducting on the edge at the same time? No, I didn't say it's topological. Sorry, I didn't say it's a superconducting edge. It's a, it's symmetry protected dissipationless edge state. Because the symmetry protection, it can, those scatterers at the edge will not change the momentum of those charge. So it's not the superconducting related at all. It's just a topological protected Taro edge state or edge state, we call it. Okay. Yeah, that's it. Sorry.
Oh.
All right. See you guys.
Thank you.
Bye-bye.